So now that we've learned about the glyoxylate shunt and how humans don't have any net ability to convert two carbon units like acetyl-CoA from fat and from ketogenic amino acids, we don't have any way of converting that into glucose. So now let's turn our attention to things like the ketogenic diet or the Atkins diet and other things that we have done intentionally to make use of our biochemistry deficiencies in order to lose weight and treat different kinds of metabolic diseases. So as a frame of reference, there are three major categories of nutrition. There are carbohydrates, there are proteins, and there are fats. When we break down carbohydrates, we ultimately make things that go into glycolysis that look like glucose and as an input. When we break down proteins, they come down into two categories. They come into these ketogenic amino acids. These are ones that are broken down into acetyl-CoA, and glucogenic amino acids. They're broken down into 3 carbon units that can ultimately feed into the glycolysis. And with fats, we break these down into acetyl-CoA as well through beta oxidation. So what happens when we stop using carbohydrates? So the whole point of the ketogenic diet is that we really dramatically reduce our consumption of carbohydrates, and we offset this with increased consumption of fat and protein. Now, this diet has some impacts on our body, which is that carbohydrates are ultimately the preferred substrate for feeding your brain and for your renal cortex and a few other tissues in your body, your red blood cells. They all rely on glucose to feed them. And so when you don't have them, your body has to make the baseline level of amino acids, or I'm sorry, glucose necessary to keep your body alive. The point of ketogenic diet is to starve yourself of this particular food substrate that your body needs, and then force your body to rely on these other forms and in order to both facilitate weight loss and to enable you to manipulate your biochemistry in a couple different ways. So let me talk a little bit about how this all works. So during beta oxidation, which is this pathway we'll learn about more later, you break down fatty acids, and the ultimate end product of that are these, acetyl-CoA. Well, acetyl-CoA can't build up in your body, and if it doesn't have a sufficient output into the TCA cycle, what will happen is your body will actually form them up into these things called ketone bodies. And these ketone bodies are like take 2 acetyl-CoAs and put them together, and this makes things like acetoacetate or beta hydroxybutyrate or acetone. These are collectively referred to as ketone bodies, and these are the byproducts of beta oxidation when you don't have sufficient draw into the TCA cycle. And we call these, these molecules here can circulate around the blood, and they can be used as a alternative starvation fuel for the brain. And there are unusual in that they're somewhat volatile. So people who are ketotic or secreting these ketone bodies, you can actually smell it. There's sort of a sweet smell in the breath, and that's from the off-gassing of acetone. So they can be used in the TCA cycle and used to support energy metabolism, but they cannot be converted into glucose. So this is what the structure of these 3 molecules, these 3 primary ketone bodies we're talking about, look like: acetone, acetoacetate, and beta hydroxybutyrate. All 3 of these ultimately come from this this condition where we're breaking down fats, and we don't have a sufficient draw into the TCA cycle. So your body uses these as a starvation fuel to feed the brain. So these things build up when people are starving, or when they have diets that are severely depleted in carbohydrates. So there are extreme versions of this. People with type 1 diabetes in particular lack the glucose, or I'm sorry, the insulin signaling. So their type 1 diabetes is a disease where their pancreas is destroyed, or at least the beta cells are in their pancreas, and they're no longer producing insulin. The net effect is that your body doesn't know it has glucose in it. And as a result, the body goes into this extreme state of diabetic ketoacidosis, where the body is producing these ketone bodies and they're circulating around in the blood. And this can be potentially life-threatening, as it can result in the reduction of blood pH, and it can ultimately cause people to go into comas, and it can be really bad. So it gets extreme in the case of type 1 diabetes. You don't see it as much in the case of type 2 diabetes, but this is something that is a potential complication of type 1 diabetes. So a ketone diet can be useful for treating diabetes and a number of other metabolic disorders. One of the most important or relevant ones we can talk about is pyruvate dehydrogenase deficiency, which we'll talk about in a minute. But there's been applications of the ketone diet to quite a number of different applications, including cardiovascular disease, weight loss, epilepsy, cancer, and some other things that's been applied to. Now, not all of the evidence in support of this is rock solid, and I'd like to go through a few of these here, case by case, and let's start to unpack them and see what the evidence is for the ketogenic diet. Now, I think one of the most clear-cut examples of how the ketogenic diet could be useful is in the context of pyruvate dehydrogenase deficiency. Now, people who have a completely non-functional PDH complex is an embryonic lethal condition. But people with reduced pyruvate dehydrogenase complex deficiency activity have some activity of the pathway, but not as much as normal people. So if you imagine, if you can't break down pyruvate properly and get it into the TCA cycle, one of the primary issues that you're going to have is that you'll have a lot of lactate in your blood, and you'll have a minimal capacity to get that carbon from glucose into the TCA cycle. So by eating fats and these alternative energy sources, you can actually bypass this inhibited step in glycolysis in the PDH cycle, feed your TCA cycle, get sufficient energy, and be okay. Now, as an anecdotal example from this, I had a friend in high school whose brother had a pyruvate dehydrogenase complex deficiency. And one of the things that was unusual about him is, as a child, he would go and raid the refrigerator and he would eat margarine directly out of the refrigerator, or butter. He was self-treating himself, or he's treating himself, self-medicating, by eating fats, because those were the things that made him feel better. So it can also be used as a mechanism for dealing with other kinds of metabolic disorders. For example, people with deficiencies in glucose transport. This also makes sense if you have an inability to get glucose into your system, that a ketogenic diet might be useful, and that it provides an alternative mechanism for getting energy into your body. And there's also been some emerging body of evidence that suggests that the ketone diet may also be helpful in treating seizures. This is more speculative than, or epilepsy, sorry. It's more speculative than some of the other biochemistry that we're talking about here. The theory is that the aminotransferase, or the neurotransmitter GABA-aminobutyrate, GABA, is actually synthesized here from glutamine, and this reliance on the ketone body may modulate, or the reliance on this fatty acid and protein catabolism may modulate the synthetic rates of GABA in the body. This is sort of speculative and less well supported, but it is something that has been connected to the ketogenic diet. Another emerging body of literature seems to suggest that the ketogenic diet may also be helpful in cancer therapy. This is again emerging theory that hasn't been well proven out yet. But the idea is that tumors are highly reliant on glucose metabolism, or they really like to use glucose metabolism when they can, and that by starving cells of glucose early on, it helps prevent them from growing and spreading. Now, this has its own problems that we'll talk about later as we get through cancer metabolism concepts. But the idea is that early on in the cancer adaptation process, this use of glucose is very, very useful for cancer cells, and by starving them of it, that prevents them from growing. So it's also been suggested that the ketogenic diet could be useful as a tool for managing type 2 diabetes. Now, type 2 diabetes is something that you develop as you grow older. What happens is that your body becomes increasingly resistant to insulin. Frequently, this is associated with obesity. And eventually, your body can't keep up with the insulin demands from your, that are needed to bring glucose into your body, and your pancreas gives up, it decompensates and stops producing insulin. So the idea with the ketogenic diet is by reducing your or restricting your catabolism, or your consumption of these carbohydrates, it sort of evades the need to have insulin in your body, and it will reduce the spiking of glucose that comes along with meals when you have meals of carbohydrates. So absolutely, the most profound effect that we have right now for the ketogenic diet, Atkins diet, is that it reduces weight loss. So this does this in it's well established empirically. We can show this in these controlled trials that people on these ketogenic diets, they lose weight. They also seem to have lower triglyceride levels, lower cholesterol, lower blood glucose, and lower lactate, LDL, which is the fat and low density lipoprotein levels in the body. So it does seem to affect your whole body physiology, and definitely allows people to lose weight. And what's going on there? Why does it work? Well, this is actually less clear-cut than you might think. There are a few things going on that are probably contributing to this. So the first off is that having fewer carbohydrates in your diet results in lower insulin levels overall. Insulin is a major stimulator of fatty acid synthesis and other pathways involved in accumulating adipose sites. So one possibility is that the ketogenic diet is affecting your body by reducing insulin signaling, and that's reducing ultimately these transcriptional pathways that are leading to the production of fat. That's one. The other thing is this: it does appear that these protein-rich, fat-rich diets suppress our appetite, and it does that through this suppression of ghrelin, which is an appetite-stimulating hormone secreted by the stomach. So it does appear that ghrelin levels are lower in people on ketogenic diets. There's also some biochemistry going on here, which is that the increase in fat intake and protein intake and fewer carbohydrates is resulting in an increased reliance on fatty acid or catabolism. And that increased fatty acid catabolism is ultimately preventing that from going into fat, and that's ultimately contributing to the loss of weight gain. And what's helping out on this too is your body does need to have glucose, does need to go gluconeogenesis. It can do that partially through the backbone and triglycerides. So although the fat itself, the free fatty acids are broken down into these 2 carbon units, the backbone is actually broken down into 3 carbon units. And so that may be contributing to these higher energetic costs that are required to synthesize glucose from that. Of course, keep in mind here that only the glycerol backbone out of the fatty acids and not the fatty acids themselves can contribute to this. So although the ketogenic diet or the Atkins diet can absolutely enable weight loss, it may not be healthy long-term. It's definitely contributes to the formation of kidney stones, urinary calcium, and could potentially contribute to acidosis. You know, it's unclear currently whether, you know, long-term habitual use of these diets is really good for people. So we talked about why we can't convert 2 carbon units into 3 carbon units as humans, how other organisms get around that with the glycolate shunt, and we talked about applications of this concept to the ketogenic diet. We also talked about some potentially dangerous side effects of overdoing it. And with that, I hope you guys are learning a little bit more about 2 carbon metabolism.